All right, now we're going to move to the next section where we're going to talk about different properties of liquids. And the first question asks us to define viscosity. Viscosity is just the resistance of a liquid to flow. Question B asks us to explain why decane, C10, 10 carbons, C10H22, has a greater viscosity than hexane, which would be C6H14. Both are nonpolar hydrocarbons with only LDF. Decane is larger, so it has more easily polarizable electrons because it's just got more of them. Therefore, it has more attractive forces, and so will have a higher viscosity. And then question C asks us to explain why glycerol has a greater viscosity than propanol. That's the answer to that is glycerol has got three alcohol groups or three hydroxyl groups, which allows three opportunities for hydrogen bonding, therefore more attractive forces, therefore more viscosity, and therefore it pours more slowly. We move on to question D. It says to explain how the viscosity of a liquid is affected by increasing the temperature. All right, at higher temperatures, molecules have higher average kinetic energy, so that means a greater fraction have enough energy to overcome these attractive forces, and viscosity, which is, of course, the resistance to flow, goes down. Question E asks us to use the diagram to explain why certain liquids experience surface tension. And here's the diagram we're looking at, and we can use this diagram to say that on any surface molecule at the surface of a liquid, there isn't really an upward force of attraction to cancel the downward force. So the surface molecules have a net downward force. And the effect on this is kind of what can be called an elastic skin. And that reduces the surface area. And it makes these surface molecules pack more closely together. This is the definition of surface tension, the reduction or the tendency to reduce the surface area of a liquid. Now, here we're looking at a comparison of a test tube filled with water versus a test tube filled with mercury. And we want to talk about the attractive forces, right? Here, clearly water has got hydrogen bonding that's occurring, whereas the only bonding that's occurring in mercury would be metallic bonding. And then question G says the meniscus of water looks like this because the adhesive forces between water and glass are more than the cohesive forces between the water molecules. And the meniscus of mercury looks like this sort of downward shaped concavity because the adhesive forces between mercury and glass are less than the cohesive forces between the mercury atoms. All right, now the next question asks us to explain how capillary action works. So when I have a small diameter tube and I put it in water, the level of water rises up the tube. Anytime you may have ever given blood, they do a little iron test, and to get the blood up out of your finger, they put a little tiny capillary tube in a pool or in a big droplet of blood on your finger, and it rises up the tube. The adhesive forces between liquid and tube walls, these tend to increase the surface area of the liquid, and the liquid surface tension tends to then reduce the area, and it pulls the liquid up the tube until the force of gravity balances these adhesive and cohesive forces. And so on a microscopic level, you can see it looks like this. Okay? We move on to the next section of phase changes. And the first question asks us to label the diagram below with the 6 phase changes. So here we've got evaporation going from liquid to gas, melting going from solid to liquid, condensation, which is going from gas back down to liquid, sublimation, which goes from solid to a gas, freezing, which goes from liquid back to a solid, and deposition, which goes from a gas back down to a solid. And it asks us to define or to note which phase changes are endothermic and which are exothermic. And all the phase changes that are associated with an up arrow in this picture require energy input, so are endothermic. That would be melting, evaporation, and sublimation. The down arrow phase changes, which would be the other three, those would be condensation, freezing, and deposition. These give up energy, so of course these are going to be exothermic. Question C asks us to define the enthalpy of fusion and enthalpy of vaporization. Here we can just say that the enthalpy of fusion is the amount of heat required to convert 1 mole of solid into a liquid at the normal melting point. And then vaporization, or the enthalpy of vaporization, would be the same effect, but at the boiling point rather than at the melting point. Question D asks us to explain why delta H vaporization tends to be larger than delta H of fusion. Here we can say that when a liquid turns into a gas, all of the intermolecular attractive forces have to be broken. But when I melt something from a solid to a liquid, that only requires some of these forces to be broken. And this means that it takes more energy to go from liquid to vapor than it does from a solid to a liquid. In a gas, these molecules are so much further apart than what they are in solids and liquids that there are no attractive forces between the molecules, and that's why all of them have to be broken. And then question E says, identify the segments of this heating curve that would involve the MCAT equation, Q is equal to MC delta T. Well, in order for this equation to be valid, a delta T has to occur, and the only segments on this curve which involve a change in temperature are A to B, C to D, and E to F. The other two regions of this curve are phase changes, and in a phase change, no temperature change exists. So that's that statement right there. All right, now we've got kind of a big calculation question. The question asks us to calculate how many kilojoules of heat are needed to convert 9 grams of ice that are solid at minus 10 degrees Celsius into steam at 110 degrees Celsius. And then they give us the specific heat values for ice, liquid water, and steam, and the heat of fusion and the heat of vaporization. So let's see if we can break this apart into pieces to solve this puzzle. And again, here's a picture of the phase change that we're talking about. 9 grams of ice is half of a mole. So let's take a look and see what we've got here. In segment AB, I have 9 grams times 2.03 joules per gram Kelvin times a 10 degree Kelvin temperature difference. And that's 0.182 kilojoules. Now when I look at the next segment, BC, this is a phase change, so it's on a per mole basis, which is why we have to compute the number of moles. But I got half of a mole times 6.01 kilojoules per mole, so that comes out to be 3.005 kilojoules. All right, now I go to CD, where I heat up the liquid water. This is an MCAT equation that we're most familiar with. 9 grams times 4.01 joules per gram Kelvin times 100 kelvins. That gives me 3.762 kilojoules. Now I boil that liquid water in segment DE, so I have half a mole times 40.67 kilojoules per mole. So again, we see that this segment is the most energy intensive, 20.335 kilojoules. And then to heat up from steam at 100 to steam at 110, would be 9 grams times 1.84 joules per gram times 10 degrees Kelvin, and I get 0.166 kilojoules. The total heat is just the sum of all 5 of these stages. I add them together, I get 27.5 kilojoules. All right, now question G says to explain the phenomena known as supercooling. So when heat is removed more quickly than the molecules can get themselves into an ordered solid structure, I get supercooling. A liquid still exists even though the temperature is below the normal freezing temperature. Supercooled liquids are unstable, and particles of dust or even a gentle agitation such as a tapping on the side of the container are sufficient to allow immediate freezing to occur. It's pretty remarkable when you see this. You can Google supercooling, and there's a number of short videos out there which show this. Step H, or question H, asks us to explain why a substance cannot become liquefied at a temperature above the critical temperature. Above the critical temperature, we denote this by T sub C, the kinetic energy of the molecules is greater than the attractive forces which lead to the liquid state. And so no matter how much we compress the vapor, there just isn't enough attractive force because of the very high temperature to cause condensation to occur. All right, now we're going to talk about section 11.5, vapor pressure. We want to suppose that a sample of liquid is placed in an evacuated closed container, and we want to describe what happens to the liquid over time. Okay, the liquid quickly evaporates to fill up a closed container, and the vapor pressure increases. And we're going to define the vapor pressure as the pressure exerted by the gas above the surface of a liquid. The molecules leave and they re-enter the liquid at equal rates. Question D asks us, what is the dynamic equilibrium that occurs in this situation? All right, so here's sort of a picture of what's happening. Some gas molecules will lose energy and condense back to a liquid, but an equilibrium will soon be reached when the evaporation rate is equal to the condensation rate. And so both processes are occurring at the same rate, and we reach an equilibrium. Question C asks us to define the term volatile, and what does it suggest about intermolecular forces. Volatility is the ease with which a liquid evaporates. If it has a high volatility, then it must have relatively weak IMFs. And then question E says, use the diagram above to explain how the vapor pressure of a liquid is affected by an increase in temperature. Whoops, I got these out of order. Question D says, which curve on this diagram represents a higher temperature? Well, kinetic energy and temperature are directly related, so the red line will be at a higher temperature. The blue line is at the lower temperature, and now we can talk about how this vapor pressure is affected. And at a higher temperature, the red line, we have a greater fraction of the molecules have the necessary energy to escape the liquid, and so they do, and so vapor pressure increases. And question F says, a liquid starts to boil when its vapor pressure is equal to the external pressure above the liquid's surface. All right, despite the fact that we're almost finished, I can't get finished in the few remaining seconds. We're going to stop this right here, and we'll come back and finish in another very short video.